Hi everyone, thank you for your interest in OoD bench, quantifying and understanding two dimensions of out-of-distribution generalization. I'm here representing the OoD bench team to present our work to you. Our work is mainly inspired by two previous observations. One is the well-known issue of neural networks that they are not good at dealing with out-of-distribution data. For example, object detectors of self-driving vehicles are unable to detect some tipped-over trucks. Models optimized with tissue slice data from one hospital are much more likely to misdiagnose a patient's condition given the data from a different hospital. Although the problem has been extensively studied in domain generalization for years, it is not until recently that most domain generalization algorithms are shown to have no clear advantage over empirical risk minimization, while the reason is left unexplained. To unravel the mystery, we find that incumbent datasets can be generally divided into two groups. On the left, we have datasets under what we call diversity shift, where the training domain and the test domain each occupies a different spectrum of image style. On the right, we have datasets under what we call correlation shift, where irrelevant features such as backgrounds and colors have opposite correlation with the labels between the two domains. We believe that they offer an explanation as to why domain generalization algorithms generally appear to be no better than ERM, as the majority of the algorithms are only able to surpass ERM in at most one of the groups. To verify our hypothesis, we start by giving a formal definition to diversity and correlation shift. First of all, we assume the data generation process depicted by the causal graph on the left, where two kinds of features, ZF1 and ZF2 together generates input X, where only ZF1 generates label Y. Then we model diversity shift as divergence in the distribution of ZF2, and model correlation shift as divergence in the distribution of Y conditioned on ZF2. To illustrate, in the middle figure, we assume ZF2 is unidimensional and denote the probability functions of ZF2 as P and Q for any two given domains. We then divide the feature space of ZF2 into subset S, where P and Q have no shared support, and subset T, where they have shared support. Finally, we define diversity shift as an integral over S that amounts to half of the summed area of the colored regions in the middle figure. We define correlation shift as an integral over T, where every integrand can be seen as the summed heights of the colored bars in the right figure, weighted by some regulating terms. To quantify the defined shifts of a dataset, we train a neural network that predicts the domain of every example in the dataset. The network takes an image and the label of the image as input, and then output the domain that the example is most likely being sampled from. We use the features extracted from the trained network to estimate diversity and correlation shift according to our previous formulation. Applying this method, we obtain the results on various datasets shown on the right. While some datasets are dominated by one of the shifts, some are found to have both shifts. Based on our quantification, we select 7 datasets and divide them into two groups, each dominated by one kind of the shifts. After evaluating 15 algorithms on these datasets, we make a discovery that some of the algorithms do have a clear advantage over ERM in one group, but none of the algorithms can outperform ERM in both groups. Here's the benchmark produced by the evaluation on the first group of datasets. We compare 15 algorithms with ERM on the 4 datasets dominated by diversity shift. According to our ranking score, the outperforming algorithms are RSC, MMD, and SegNet. And here's the benchmark produced by the evaluation on the second group of datasets. Note that the previous outperforming algorithms are replaced by VREX and Group DRO, which are both worse than ERM previously. We conclude our presentation with 3 recommendations for future research. First, evaluate OoD generalization algorithms on 2 types of datasets, one dominated by diversity shift and the other dominated by correlation shift. Second, investigate the nature of distribution shift in OoD problems before designing algorithms, since the optimal treatment for different kinds of distribution shift may be different. Third, design large-scale datasets that more subtly capture real-world distribution shifts, as even imperceptible shifts can be conspicuous to neural networks.